Hello everybody. So in this video we are going to solve one more example on the multi-unit system, and we are going to discuss the or we apply the same things. I'm not discussing anything new here. It's just one more example. It contains more details or more detailed process, which makes the topic more clearer when we solve it. So for the process that we see here, we have two extractors, extractor 1 and extractor 2. We have two feeds to the first extractor, and then we have one feed to the second extractor with the product from the first. And then we have two streams coming from the two extractors. They are mixed together and then fed to a distillation column. And we have some information that are already put on the flow sheet. So what we want to do now is we are trying to calculate all the missing information. To do this, we have to first do the very first thing, which is doing the degrees of freedom analysis. So we agreed before that the degrees of freedom analysis will be done in a form of a table, and in this table we will have columns, one for each unit, and rows, one for each parameter in the degrees of freedom calculation. So if we look at the, we will take them one by one. We'll start with extractor 1, then extractor 2, then mixer, then distillation column, and then the overall loop. So for extractor 1, we have the streams that we are looking at are 1, 2, 4, 3, and 4. So we have the number of variables. We have 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 variables. And we have the number of given variables here. We have 2 in this stream, 1, so this is 3, and we have 1 here. And this is something that is kind of confusing here. If you take a closer look at stream 3, you would see here that we have two information that are written. One is 0.275 and one is 0.725 minus xw. And if you look at this would be just sigma x equals 1. It's 1 minus this minus this. So 1 minus 0.275 is 0.725. 1 minus this is this, minus xw. So this is actually just something that's put to confuse. It's not adding anything new. We already know this without even being told that. So we have only one information here. Again, so the total number of information are 2 given information, 2, 3, 4. So we have 9 variables, 4 given variables, and we have 3 equations, A, W, and M, and no additional relations, and this will make the degrees of freedom equal to. So extractor 1 is not solvable with the given information. So let's move to extractor 2. We have streams 4, 5, 6, and 7. So we have a number of variables, 3, 3, and 3, so this is 9, and we have 1 here, so this is 10. The number of given variables are 1, 2, 3, 4, 5, 6, and we agreed that the last one of the mole fractions or mass fractions is a dependent one, so we don't count it. So we have 2, 3, 4, 5, 6, so we have 6 variables, and again we have 3 equations, so this is and no additional relation, so the degrees of freedom is 1. Now let's move to the mixer. For the mixer, we are looking at streams 3, 7, and 8. We have 3, 3, and 3, so we have 9 variables. The given variables are 1, 2, 3. So it's 6, 3, and we have 3 equations. 9, 3, and 3 equations, so we have degrees of freedom is only 3. And finally, for the distillation column, we are looking at streams 8, 9, and 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 variables. We know only 2, so it's 9 with 2 given variables. We have 3 equations, so this makes the degrees of freedom equal to 4. So it seems that none of the units is solvable with the given information, so we can try one more thing, which is the overall loop. So if we look at the overall loop, we would see that we are interested in streams 1, 2, 5, 6, 8, 9, and 10. So these are the only streams that are crossing the boundaries. So now let's count the number of variables. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. the number of given variables are 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 variables and 3 equations, so this makes the degrees of freedom 1. So with all the information that we have, we reach the conclusion that none of these units is solvable with the given information. And this is something interesting, that you can do this or reach this conclusion without starting. And again, this is what makes the degrees of freedom very, very useful and very helpful, is that it's saving us a lot of time that we could put in just solving equations without being even solvable with the given information. So now we have to find some solution to this. So one thing that we can do is to look for another combination of units that might work or will have degrees of freedom equal 0. So if we are looking at this, we should be looking at a loop or part of the system with interconnected units, where we have as many given information as possible. And if we look at the given information that we have, they are primarily in streams 1, 2, 5, 6, and we have some informations in streams 3, 7, and some in stream 9. So they are primarily around these 2 units. This is where the most of the given information are. So we can try this loop as a new system, which is the 2 extractors, and we can try doing the degrees of freedom analysis for these 2 extractors together. And if we do this, we'll see that we are looking at streams 1, 2, 5, 6, 7, and 3. 1, 2, 3, 5, 6, 7. Now let's count the number of variables. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 variables. The given variables are 2, 3, 4, 5, 6, 7, 5, 6, 7, 8, 9, 10. So we have 13 variables, 10 given variables, 3 equations, and this makes the degrees of freedom equal to 0. So this is one trick that we can do in case we have a system like this and we don't have any unit that has 0 degrees of freedom. We can find the combination of units, and this is going to solve the whole thing, because by doing this we can have a plan for the solution. So if I solve these 2 extractors, I'm calculating the flow rate in this stream and the flow rate and the missing composition in this stream. So I'm adding 2 information to the first extractor, which makes the degrees of freedom for this extractor 0. And we add 1 information to the second extractor, which makes the degrees of freedom of the second extractor 0. And these 2 and 1, which are 3 information, are also given to M1, which is the mixer. So we have 3 extra information to the mixer, which makes the mixer solvable. So after solving the 2 extractors together, we can solve one of the 2 extractors, and we can solve the mixer. And of course, one of the 2 would be enough, because if you solve any one of the 2 extractors, we can calculate stream 4, all the information in stream 4, which is makes the other extractor done. And finally, we can go to the distillation column, but we'll see here that you can add 3 information to the distillation column, and it still needs 4 information. So 3 information is not enough. It still needs 1 extra information to be assumed. But for the time being, we can solve these 3 units with this, starting with this green loop. There is one other option. I will just mention this, and you can try it yourself. It's going to be a good practice. So you can try starting with extractor 1, extractor 2, and mixer 1. So this loop is what we have here, and this loop is going to have 0 degrees of freedom. And if you start with this loop, you will solve it. Then you solve the mixer, then one of the extractors, and then again you have one assumption for the distillation column. Anyways, there are more than one option, so you can try whatever is more convenient for you. So what we are going to do now is we will start with the 2 extractors. If we solve the 2 extractors, we can apply the total mass balance. So if we apply the total mass balance, it's going to be M1 plus M2 plus M5 equals M3 plus M7 and M6. And we can substitute with the values that we have, and we will end up with an equation or equation in two unknowns, which is M3 and M7. Now we have we said we have three equations, so we used one already. We have two other equations which we want to pick two of them. And when you pick the two equations, you have to be smart when you pick the equations. It's not just any random equation that you pick. You have to think of the equations that would make your solution easier. So I have here an equation of one equation and two unknowns. So if I have another equations in the same two unknowns, it's going to be two equations and two unknowns, which is very, very simple problem, other than having three equations and three unknowns. We know that we have three variables to calculate: M7, M3, and XW3. So we have three variables. But if we can have the solution put in two equations and two unknowns, and then later we calculate the third variable, this is a very, very ideal case. So if you look at the A, you would see here that you have A here. You have no A here. There is no A here. So we have A in 1, 2, 3, 4 streams, and which is the very important part, that the four compositions of A in these four streams are known. So you know the mass fraction here of A, the mass fraction of A here, the mass fraction of A here, and the mass fraction of A here, which is very, very good news, because if you apply the equation of A, then you will have another equation with the unknown variables only are M3 and M7. However, if you try to use W, then you will have W here. There is no W here. You have W here. You have W here, but there is one extra variable here, which is XW3, which you don't know. So you cannot solve the equation of W with this equation. If you apply the equation for M, you have two M's here. You have one M here. You have one M here. You have one M here, but still you don't know the value of this XM. So again, it's introducing one more variable here. So it's better to go with A, and then by the mass balance we can, or solving the two equations, you can get M3 and M7, and you can substitute with the balance on W or M, whatever you like, and we can find the value of XW3, and we can calculate XM3 from XW3. So this is for the first part. The second part is, and now let's update the degrees of freedom table. I now updated the streams, so I put all the information that were missing after calculating the streams or the variables, and now we can update the degrees of freedom. We said that we have 0 degrees of freedom for extractor 1, we have 0 for 2, and 0 for 3, and now we can solve extractor 1, for example. So for extractor 1 is going to be a piece of cake now. It's in equals out. We know all the ins, so we are just or two ins and one of the outs. So we are only calculating the extra or the second outlet stream. The total mass balance would be direct substitution to get the value of M4, and the component mass balance will be again equation in one variable. It's very straightforward, so I'm not wasting time in the details. You have the equations already in the slides. One thing that I really emphasize here is that you have to do the calculations yourself. It seems very simple, very straightforward, but you have to go through the process yourself, step by step. The solution of equations simultaneously sometimes needs some training, so you need to be well trained on this, not just by looking at the steps. So after solving this, we can solve M1. So by solving M1, we can, again, we know everything about stream 3 and 7, so we can know everything about stream 8, and by doing this we can find the compositions and the flow rate of stream 8. Now by doing the updating the degrees of freedom table, you would see here that the degrees of freedom of distillation column is 1. So we have to assume something, and this assumption is up to you. You can assume M9, you can assume M10, you can assume these. Let's just zoom into the distillation column. So you can assume this flow rate or this flow rate or any one of the compositions. I personally prefer to assume one of the compositions because the assumption of a composition will have a very narrow range from 0 to 1, which is not the case for the flow rates. And it can be very logical assumption. For example, for XA here, you see it's 97%, and we know distillation separates components based on their volatility. So you'll have a component that is very rich in the top product, and it's going to be very small amounts in the bottom product. So it's expected that A in the bottom product would be very small ratio or percentage, can be 2 or 3%. So if you assume 2 or 3%, 4%, for example, this is a very reasonable assumption, and it will make the solution very straightforward. So this is all for this problem. And in the next problem, we will talk about one other thing that we need to know about the multi-unit system. So I'll see you then. Goodbye.